Hello everyone. Our topic today is full wave rectifier, which is chapter 4. Okay, full wave rectifier, which is single phase. So single phase, full wave, uncontrolled rectifier. Last time we took the single phase, half wave, uncontrolled rectifier. This time we'll take single phase, full wave, which we will use the 4 diodes or the bridge. Okay. So it's in page 111 in your textbook, and in your notes, the topic is in page 17. Okay. So let's see what's going on right here. And this is the full wave. So let's look at the current. This is 4N, which is line and neutral, and this is the positive here, and this is the negative. So the positive will go here, cannot go down, it will go up. So this one here will be diode number 1, power diode number 1, and this one cannot be, because you know the current cannot go from cathode to anode, it goes the opposite. So the current will come here, it cannot go this way, it will go through the load right here. So we can say here that I source here, I source same as I diode 1, same as I out. Then, which path it will take, this or this? Of course it cannot take this path right here, because this line right here is positive charged, so this will be an open circuit, so it will take this path. So this is diode number 2. We will name the diodes according to the sequence, okay, and then it will go back. So now in the output, this is V out DC, this is my out, this is my V source, sinusoidal wave. As I told you before, we will start from the peak to draw. So I'll go from the peak here to 0. That's what I get up to now. Half wave. Up to now, half wave. What we have done with using the bridge, we open the path for both positive and negative. In half wave, we only have one path, which is the positive will flow through, the negative will not. That's why we have a half wave. And even in lab, we noticed that if the source is 100 volt, the output is 50 volt, which is, we lost half. Okay, that's what we get up to now. This is, we can call this one here diode 1 and diode 2, which is this and this. Okay, same thing with the current. The current will be the same wave, but the peak is half, approximately half. So we'll go from here, and this one here is I out DC, the red. Let's see the other part, which is the negative. The negative will flow, now we open path for the negative, so the negative will go from here, it will go from here. It cannot go down, as we know, so it will go up. So this one here, this diode right here, or this power diode is diode number 3, and then no, look at here, guys. They go on. This is positive, negative. I'm talking about the load V out. This is V out. Let me use the black, since I am drawing the V out with the black. So this one here positive, and this is negative, which is V out DC across the load. So now look at the direction of the current that goes to the load. They're coming from one direction. That's why we will have everything in the positive direction. That's why we convert it. That's why we call it rectifier, because we rectify, we convert from AC into DC. Let's see here, let's finish. Okay, then it will come here. It cannot go there because now this side right here is positive charge, is fully charged, is charged. So the polarity will flip right here, and this will be an open circuit. So it will go through this diode, and we call this one 4, and then the circuit is closed. So now we have another pulse, which is here in the positive. We start with the peak. Okay. And then the negative. This one here is diode 3 and 4. So this is diode 3 and diode 4. And the current, same. It will be half peak, but the same wave. We know from before that the current follows the voltage. Okay. Again, why we have both here pulses in the positive? Because that's what we have done. We designed the bridge to open a path for the positive, which is the black here, and the current came to the load from the positive direction. Then we open a path for the negative, see here the negative, and then same thing, the current came to the load from the positive direction. That's why we have that one right there. And we can say here that I source, here I source in the red, I source, same as I diode 3, same as I out. Of course, same as I diode 4. Because diode 3, same as I diode 4. And here, I source, the black, same as I diode 1, same as I out, same as diode 2. I diode 2. Okay? So what's I out? I out is the addition of both. So if I out equals 2 ampere, then I diode 1 equals 1 ampere. And since I diode 1 is 1 ampere, I diode 2 is 1 ampere because it's one path. And then also I diode 3 equals 1 ampere. Okay? The drawings are right here, guys. You can look at them on page 112. Okay. Okay, so that's the V out diode, V out DC and I out DC. Okay, if we want to draw the voltage across the diode, which is the voltage across this is called V diode 1. Of course, it will be the same as V diode 2. Because if there's current through this diode, means there's no voltage, as we know from before. Because if you try to measure 2 points which are the same, there is no potential difference. And we know that V diode 3 same as V diode 4. Okay? So let's look at those two right here. So this one here is V diode 1 and 2. 1 and V diode 2. 1 and 2. So we're looking at this part. We're not looking at that, right? Let's see here. The diode is conducting, the diode 1 and diode 2. So since it's conducting, it's 0 right here. 0 up to this point. So this is 0. Okay? And what's left? This is from the source. That's what's left. So we go from the peak. Okay? And we go from the peak. That's V diode 1, V diode 2. The voltage across this and this. When it conducts, which is here, it conducts at 0. And we know from before, guys, that this point here is alpha, which is 0, and we call it also firing angle. And this point here is beta, and we call it commutation angle. And the conduction angle is between this, which is alpha, and this is called conduction angle here. This is gamma, which is conduction. And the conduction angle here is 180. Okay? In this case, this one here, this point is 180, equals 180 here. And same thing, this is equals 180, and this is equals 0. And we know that conduction angle equals beta minus alpha. So this one here equals 180 minus 0 equals 180. We did this last time. Okay? Now let's look at okay, I'm trying, because I want you guys to see the drawing, that's why I'm drawing it this way. Okay, now I want to draw V diode 3 and 4. V diode 3 and diode 4. So we should look at this one. This one is conducting, which is this case, it's 0. So I go from here, and that's, I know that this is 0 here. 0, 0. 0, 0, 0, up to this point, sorry, up to this point here. 0. That's 0 from here up to here. What's left? What's left is this. Of course, we are assuming here, we are assuming that the source is like this. That's what we are assuming, that the source is like this. That's what's left. Now this is 0, but we will be assuming that the source is like this. Okay? Because this one here is the negative. It starts the opposite. It does not start here. It starts from here. So the negative starts from here. Okay? That's the negative, starts from here. Because this one is the positive, it starts from here, but the negative, it starts from here. So that's what will be left. And this is 0. Okay, that's V diode 3 and V diode 4. Again, I don't want you to be confused. Yes, they're both in the negative. Because this one here is the positive. V diode 1 is the positive, which is same as this. But if we come to the negative, we're looking at it from here. So it starts from here, the negative. Okay, that's why we have the shift. So that's what will be left. So that's the voltage across the diodes. Okay? Of course, that's with resistive load. I want you to pay attention, guys. This is with resistive load, okay? With inductive load, with inductive, this is all with resistive load. All this with resistive load. With inductive load, the only difference is the current will be smoother. So the current with inductive load will be like this. Okay? So this one here with inductive RL. This one here, the dots. The rest is the same, okay? When we connect inductor to the circuit, and that's what you will do in lab, you will notice that everything is the same. The output voltage will not change. Those will not change. The only change will be in current. And put this note, please. If notes, okay, to get, where is this? To get straight DC current, increase or make inductor very, make inductor huge, big, okay? Or we can say, or sometimes we say infinity. So if there's a question comes to you saying that, assume that the inductive is infinity, it means that they're telling you that the current is straight DC. You make it straight DC. Okay. Last time in half wave, I asked you a question, what would be I source? And we say, I answered the question. I told you that I source would be same as I output because the connection is in series and it's one path. So the positive will go through the diode, and that is it, which is only even the pulse of the current will be half, same as the I out. But here, what will be I source? I source will be sinusoid. It will be positive and negative. It will be like this. And it will be negative also. Okay? Why it will be negative and positive? Because we open path for the positive, which is the black, and we open path for the negative. So we open path for both positive and negative. That's why the sinusoidal will continue. That's I source. Okay? That's I source. In your lab, you're gonna do the same as what we have done in experiment number 1, which is the single phase half wave. You're gonna do the same here. Let me just show you the lab, guys. In your lab, you're gonna do the connection. You will connect the circuit right here, which is the bridge, okay? And then you're gonna fill the table right here. You will notice that now the voltage, the source will be same as the output because it's full wave, okay? And the conduction angle will be the same because there is no change. It will be the conduction angle will be 180 for resistive and inductive. And the drawing, you're gonna draw the voltage and current here. That's for the resistive. You guys see it, same as that. And then for the inductive, you're gonna add the inductive in series with the resistive load, and that will be the change, which is the current. The current will be smoother. Okay. And then this one here, the last one, will be for the center tab. Just I know you guys took the center tab in electronics, and it's like 2 half waves together. Center tab will be the same, but the peak will be half. It will be the same drawings, but the peak will be half. So that's here. See here, that's the peak for the voltage, and that's the peak for the current. So it will be the same as this one here. without the inductive, but the peak is less. So the voltage will be here and the current will be half. That's the center tap. So after you're done in your lab with bridge, rectifier, you're gonna do the connect the center tab. Okay, and that's the center tab. And you need to look at it in your notes. This is the center tab. I will not explain it right here. And you will look at it also in your textbook. This is your textbook right here. Okay, this is your bridge. Either this way. This is the way I think they explain it to you in circuit 1 or on electronics. And this is this way. It doesn't matter. It's just, you know, figures. And this is the drawings right here. This is the source and this is the V out, same as this, but this is enough. If you understand this one, you'll be okay. And this is the center tab. You will notice that the peak is less, okay? The peak is less, and that's for the full wave. I don't know if I have any other thing that I need to explain to you. Let me look at the. Okay, guys, I want you to look at example 4-1. Look at example 4-1. Okay, please look at example 1 on page 117, which is 4-1 in page 117. Look at that. Okay. Let me just go over the center tab quickly. So if I put the center tab right here, okay, so I will have a source, okay, then I will have transformer, guys, then I will have a transformer right here, okay, and then I will have a power diode, and I will have a power diode right here, okay, and then you will have a center tab. You will split this into halves, and then you will have a load right here, okay, like this. So it's like 2 half waves, okay, it's like 2 half waves. So this is, we are assuming that this is 1-to-1 ratio, and this is 4N, so this is 120 volt, okay. If this is 120 volt, guys, this will be 60 volt, and this will be 60 volt, okay. That's why we said that the peak will be half. So 60 volt and 60 volt. So what will happen then? The current will flow through here, okay. Cannot go there, because the current cannot flow there. That's will give you one pulse, and same thing with this. It will go through here, and it will give you the other half pulse, okay. So that's the center tab. So the center tab, if I come and draw the center tab, okay, I can draw right here. So center tab, if I draw the V out DC, of course this is center tab. So I will have the peak. You see the peak here? 2 boxes for the volt. I will have it only 1 box. So it will be like this. Okay? And then it will be like this. Something like this. Okay? Sorry for my drawing, because I want you to see the drawing, that's why. Okay? And then the other pulse will be here. So something like this. Okay? And something like this. That's the V out. The current will be half. Okay? The current will be half. Something like this. That's the center tab. So it will be the same, but the peak is half. So if they ask you what's center tab, you can say it's like two half waves merged together. So this is a half wave, and this is a half wave. What I want you guys to read in your textbook, please, it's chapter 4, okay, please. So page in your textbook, and text book, look at textbook page, pages 111 to 118 to 118. Okay, notes, pages, in your notes, not that much, page 17 to page 19, 17 to 19, okay? Sorry, to, no, not to 19, to 21. To 21. Okay. I want to make a note right here for the equations. This point is very important point, guys. Last time I told you about the equations for the half wave. Please, I want you to look at this. And for the half wave, I will repeat this. For the half wave, okay, this is for the half wave last week. Those are the equations, okay? Look at those equations, make sure you understand those equations. This is for resistive load only, okay? Page 11. For the inductive load for half wave, it will be the same except the V out DC. It will be different equation, which is this in page 112, which is V out DC, V max over 2 pi times 1 minus cosine beta. This is the only difference in equations for inductive load half wave. So if you are looking for the equations for inductive in half wave, those except this one right here. This is for the resistive load. This one here is for the resistive load. For the inductive load half wave is this. Okay, so now that's for half wave. For full wave, this is for full wave here. Full wave equations, you're going to find out that almost the equations are the same. The efficiency, the ripple factor, form factor, P out RMS, which is Ohm's law, I out RMS, V out. This one here is different, the V out. All the time, this one will be different. This is now halfway, the V out for half wave. V out DC equals 2 V max over pi. And I out DC, Ohm's law, V out over resistance. And the power is Ohm's law, voltage times current. And the V out RMS is V max over square root of 2. Okay, this is, you will find it, different than the rest. And same thing, this one here. So pay attention to those, V out DC and V out RMS. Most of the other stuff, equations are the same. Okay, those equations right here are for full wave equations for resistive load and inductive load, no change. For resistive load and inductive load, they will be the same equations. Please understand this, and if you have any other question, we have either you can ask through the Telegram or through the live session we will have next week. We're gonna have live session next week at Tuesday at 4 or 5. So if you have any question, we can go over it. Okay, that's all I have for today, and see you next time.